very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you'll be fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We by pounds on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
You're welcome, class. Today, we'll continue with our series of lectures. We've been talking about general topology for some time, and we've considered the basic concepts of general topology. And in the previous classes, we have dwelt on spaces that are abstract in nature. But now we want to go into the specifics and want to see how to apply topology to real spaces, and particularly the vector space Rn, which we call the Euclidean space. Of course, you know that R here is the real line, and then you have it in n tuples. And then, of course, you know that this is same as having R cross R in n copies, okay, n times. So when you multiply, you carry out the Cartesian product. We call this the Cartesian product. Cartesian product, okay, of Rn in n places. So we have the Rn space. This space actually, if I'm to write an element or a point in this space, Rn is defined as the space of vectors in n tuples. In n tuples, such that each of these x lies in R, okay, where k here ranges from 1 up till n, okay? So this is Rn. Now, we want to look at some nature of this Rn space. If we are to consider when n is equals to 0, for instance, when n is equals to 0 here, when n equals 0, we mean R0 is just simply a singleton made up of a point. You know, I've told you in previous classes that when we are looking at general topology, we are looking at Pointset topology. But this is a point. When you have R, this is 0, not degree, R with dimension 0. And if I were to define a topology, let's say a topological space on R0, R0, that means our topology on X here is simply going to give us the trivial topology made up of the empty set and X, which is just a point, So that is the kind of topology we can define on R0. Then we can also have situation where our X, for the case when n is equals to 1, then we have what we call the real line. you can define a topology on the real line. The real line is simply defined as the open interval from negative infinity to positive infinity. Okay? And you can define some open sets on the real line here. We take a look at our number line, for instance. The number line, which stretches from negative infinity and has a center here at 0, and then you have the positive infinity. So you can define so many open sets inside, because in fact this one is an open set. But how do we define an open set on the real line, which is what we have here? This is our real line. Okay? Here you only had a single point. But you know, when you are dwelling on the real line, you can pick as many points as possible on the real line. But let's be particular about 2. So we may decide to pick a point A and a point B. Okay? We pick a point A and a point B on the real line. And if we say, okay, let A and B be points on the real line, we want to define an open set such that A is is strictly less than B, such that A is strictly less than B. Of course, you know that this is less than this, as it is being ordered on the real line. Then, a set, call it S here, is open. That is, an open set is open in R1. If you can create an open interval that is bounded by A and B, okay, this is an open interval, okay, that is contained inside S. Then all open sets in the real line are defined as open interval. When we say open interval, of course, you know this is A, B, simply means all elements X, such that A is less than X and X is strictly less than B. So when we are talking about open sets in this, the topology on R has open sets to be sections. We call this as sections, open sections, which contain open intervals. Sections themselves are intervals, open intervals themselves. For instance, I can decide to say, okay, S is equals to alpha, comma, beta. Okay? So if this is contained inside here, it simply means that where if I say A, B is contained inside alpha, beta, I simply mean that A is the least upper bound, the least upper, the greatest lower bound of alpha, and beta here is, the least upper bound of this. So that means that alpha, so this means that A is simply going to be equals to the minimum, or let me say the maximum of the pair, of A and alpha, okay? And B is going to be the minimum of B and beta. So that is how you look at an open interval contained inside another open interval. Now, so we want to see, and inside this, there will always be a point. Okay, so you can define a point. You can define a point if there exists a point x naught contained inside this open interval, and this open interval is contained inside this section. Then you say S is open in R1. We are going to see some examples, but before then, we want to see how we prove the topological axioms on the real line. Let's take a look at some remarks on the topology on the real line. Okay? Let's say we look at a remark here. Okay? We claim that the Euclidean topology thus the topology on R1 is a topology. Okay? For this statement to be true, then this set here, or class of sets, must fulfill the three axioms of topology. Namely, there must be empty set as well as the whole of R in the set of topology. So, proof of this remark, we say, okay, we show that R1, which is the real line, is a member of the topological class of R1. Okay? The whole of this must be here. So for this to happen, we put A to be equals to x minus 1, and we put B to be equals to x plus 1. If that is so, then we can claim that x will lie between this and this, because x will be in between x minus 1 and x plus 1. So that means that x will be contained inside this open interval, this. And this is just a trivial part of what we see, is just a small part of what we see in the real line. And of course, this is the definition of an open set. So that means that this real line, the whole of real line, is inside the topology on R1. So that means that R1 belongs here, belongs to the topology on it. Okay, now let's see. Let's go further. As for the argument for empty sets, we cannot argue because an empty set is by default a member of all sets. An empty set is by default a subset of all sets is by default. So there is no need so by this we mean that R1 is open by what we have done here. Secondly, when we say something is by default, we mean that it doesn't even need proof. It's a generally accepted statement. So the empty set is contained in R1, is by default a member of R1. Thus, it is also open. Okay? is also open. So this is open. Now we want to look at the second axiom. The second axiom, which is what we call the arbitrary union of sections. Now let's us have a set of sections, just like this one. We have arbitrary union in front of us. So where small j lies in capital J, okay, for some indexing set J, okay. Then we can see that there exists X belonging to R1 if for each J inside capital J, J inside capital J, such that X is inside A, B by definition of a section. So if you can have such, then it will also imply, okay, thank you. It will also imply, this will also imply that if A can be contained in at least one of these, if A can be contained in at least one of these, then if you take the union of this, you will still find this inside the union of this for whatever number of J's you have. So this also implies that X belongs to A, B, which is also contained in arbitrary union of SJs. So the condition for A, B to belong to the arbitrary union of this is that it belongs to at least one of them. So if it can belong to at least one of them, then it can be in the union of all of them. So by that, we have seen that the axiom of arbitrary union is fulfilled for these open sections or open sets, which we otherwise call open intervals. Likewise, we can look at the finite intersection of these sections, okay? For finite intersections, consider two open sets, S1 and S2, which of course belong to R1, okay? Such that Y belongs to A, B. This is an open interval. Y lies between A and B. Where this is contained inside S1, and we also claim that if Y also is contained inside C, D belonging to S2, then it means that Y is contained in intersection of both of them, okay? So that means that Y is contained. This implies that Y is contained in, we are not going to use these two intervals. We'll use E, F. I'll tell you the reason why very soon. And where this is contained inside the intersection of S1 and S2. Now, E will actually be the minimum, the infimum, otherwise known as the maximum, between A and C. okay, the greatest lower bound among the two. Okay, the greatest lower bound among the two. And then F will be the supremum, otherwise seen as the maximum between B and D. So when this is defined, then we claim that finite intersection is fulfilled. So the three axioms are already fulfilled. Empty set as well as the whole of R is in R. And then arbitrary union of sections is also fulfilled, and then the finite intersection. So with this now, we are good to go with what we are to do today. Now, we are going to look at some simple propositions. Some simple propositions. Why do some open intervals, why are some intervals open in R, and why are some others closed? This is what we will look at in what follows. Let's quickly take a look at a few. I'll make some claims, some theorems. Let's see a theorem here, a theorem which is in the material you have with you, 3.12. The open intervals, are R infinity and minus infinity R are open in R1. This I will need to change my marker so that for visibility. So let me do that. So for legibility, we've changed our marker. So let's see. We want to show that these open intervals R infinity and minus infinity R belong to, are open in the topology of R1. So how do we achieve that? Okay, let's look at a very simple proof. Very short and simple. We need to follow definition. In this course, definition is very, very important. And whatever definition you are given at the beginning of the course should follow through whenever you are attempting to answer a question in this course. Now, for this, now we say let X belong to R infinity. Of course, you know, when we have something like this, it means that you have your real line is positive infinity, and then you have a point R on it, and it is open. You don't shade an open point. Okay, so we are looking at the point that lies between R and infinity. Now, how do we achieve the answer here? So we want to see, what if your X lies somewhere here? Suppose your X lies somewhere here. How do you achieve the consideration of an open set there? So what we simply do, we say let's, then we seek. If X lies here, then we seek A and B lying in R1 such that A is less than B. And if A is less than B, we can, then you can have an open interval A, comma B. Okay. So if that is the case, we want to see that this A comma B, the open interval A comma B, is contained inside R infinity. So how do we achieve that? That is where we are going here. Now for we to achieve a point like that, we can see that by setting A to be equals to R. Let's assume that A is equals to R here. If A is equals to R, that means the A here and R here coincide. Let's now say that let me assume this. Okay. Let me assume that A is less or is equals to R. And B here is equals to X plus P. Let's say B is equals to X plus a small positive number where P is greater than 0, greater or equals to 0. Then it means that we can say that X lies within R and what? X plus P. And X plus P, we know that can never reach plus infinity. This is less than what? Is less than plus infinity. What is this by implication? That means that X here lies in an open interval, A comma B. And A comma B is contained in R comma infinity. So, what do we have? We are able to achieve our goal that X lies inside A comma B, and A comma B here is contained inside R comma infinity. So as we have done for the positive, we can also achieve for the negative. That is the other side, the other flip mirror side of the real line. Now, let's assume, let X also, on the other hand, belong to negative infinity by R. In other words, what are we saying? That you have your number line. Towards this side, you have minus infinity, and then here you have an open point, R. Okay? So that means that what we are looking at is anything below R, anything to the left-hand side of R. So if we want to assume what happens if X belongs here, if X belongs to the negative side of the number line, what happens? Now we also need to follow what we have done here earlier to achieve our goal. Now this is what we do. For instance, you say, okay, let's B. We are going to start from the right-hand side because normally B is on the right-hand side, and then we look at the left-hand side. Now let's see what happens. Let's say that B here is equals to X minus P. X minus P. And A is equals to negative infinity. Or let's not be rushed. Now let's look at this. Of course, you will believe me that, let me even assume, okay, that of course if this is the case, then we know that X minus P, which is B, is less than x. This is less than x. You will agree with me that if you take away any value from x, let's say p, which is a small positive number, if you take away any value from x, it will be less than x itself. Okay, and let's now assume that x is less than r, because we want x to be contained inside this open interval. Of course, whatever you get here, if p increases, let's assume that p is going towards infinity, is increasing. What will happen? This number will be going from, it will be decreasing, it will be going on the negative side towards negative infinity. So by this now, we can now see that x lies, so we can now assume that this now, that x lies in a, you have a r positive. X lies in minus, it lies in a comma b. Of course, you will always get a number that is less than, if you get a to be less than b, you will always get a number that will lie between b and negative infinity, which we assume a, and this is contained inside negative infinity r. And that takes care of that proof. So we see that on both sides, you can see that you can prove that this is open. So this is open as well as this. Okay. Now, we are ready to look at a counter example. And we want to make a claim here that the union of two open intervals is not necessarily open. The union of two open intervals is not necessarily open. It's not necessarily an open set. This is the reason. Let me give you an example. In other topologies, generally, you will say union of two open sets is open. But it's not always so in the real Euclidean space of R1. Let's say this is a counter example. When do we say that a set is open? If you can define an open interval inside that set, you say it is open. Now, let's look at this now. The union of two open intervals. Let's say this is 1, 3. This is an interval between 1 and 3. And then we have another open interval here, 5, 6. Can we claim that this union is open? That is a big question that we want to see. What will this give us? This is a set. Let me put it in drawing. We have our real line, and then we have a 0 mark here, and then you have 1, and then you have 3, you have 5, and then you have 6. The open interval between 1 and 3 is this. The open interval between 5 and 6 is this. Join them with a line. But can you define any interval that will lie within this without any breaking, without any separation? So you will see that that will always almost be impossible. This is not open. It's not open. Open because on R1 because there does not exist any open interval a comma b that is contained in this open interval 1, 3 union 5, 6. So, though you are taking their union, but they don't have any meeting point, no continuity, there's discontinuity, there's a breaking between the two intervals. So you cannot get an open interval that can be found within this interval. Now, I go to some very tricky and small theorems that we shall be considering. Now, I want to look at a singleton of a point. We want to lay claim to a theorem, want to make a claim of a theorem that the set containing a point A, for instance, in R1 is closed in R1. Now, of course, you remember that I told you that for you to obtain a closure, a closed set from an open set, you have to consider what we call the complementary or relative complement of the set. Let's assume that U is open. If U is open, then the closed set corresponding to U is simply X take away U. That is what we know by closure. So we say that this is closed if U is open and you take it away from X. Okay, so for us to claim that this is closed, we want to take away this set from this real line. Of course, we know. Let me put it here. This is my real line. I'm using diagram to illustrate so that it will be very clear to everyone that is looking. Now, this is the point A. That is the point A. If you take away the point A from the real line, what happens? Let's remove the point. Remove the point A from here. Okay? Then, what do we have? We have positive, negative infinity here, positive infinity here. This is the real line. And then you have removed the point A. The moment you remove it, the shaded portion will become what? It will become open. It's no more closed. Now, what happens from here to here, and what happens from here to here? You will see that you are going to get that R, take away the singleton, is equals to the open interval minus infinity A union the open interval A plus infinity. And we have already shown that A minus infinity and A plus infinity are open. And this is the union of two open sets. And therefore, the union of two open sets, open, union, open, here equals open. Thus, if R take away A gives you an open set, then we can conclude that A is closed. Hence, the singleton A is closed as required. Okay. Okay. Now, let's take a look at some family of sets, or let me say the set of integers. We want to lay claim that the set of integers is closed. This is another theorem. The set of integers, okay, of course, this is a subset of R1, is closed. Okay, so let's see what will make our claim correct. Now, we know, let's look at the proof, that Z, which is the set of integers, is defined by dot, 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 minus 3, minus 2, minus 1, 0, 1, 2, 3, dot, dot, dot. Okay? In some textbooks, it is written as 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Okay? This is the set of integers. But you need to know that when you draw this on your real line, when you write this on your real line, you have the set. You have your 0, you have the plus 1, plus 2, plus 3, and so on. You have the minus 1, you have the minus 2, you have the minus 3, and so on. To the left, to the right, and at the center. So you have the set of integers. Now, what happens if I'm considering all these points I'm shading here are integers. What happens if I'm to remove these points from the real line? All of them will be open. And what are we going to get? We are going to get, so let's remove all this, remove all this, remove all this, remove all this, remove all the integers. What are we going to get? You will get minus 3, open, minus 2, open, minus 1, open, then you 0, open, plus 1, open, plus 2, open, plus 3, open. Of course, what are we going to be left with? We are going to have between each of these open intervals. And therefore, we are now going to have, just like we did when we were dwelling on singleton, we are going to see that we are going to have the union of the open interval between minus 3, minus 2, union minus 2, minus 1, union minus 1, 0, union 0, 1, union, and so on. So, what is this telling us? These are, take away the set of integers. What you will have will be an arbitrary union of open intervals. Therefore, this, okay, can now be written as, okay, the union. Let me put this as n equals minus infinity to plus infinity, because it stretches to the left and to the right, of the open intervals between the even and the odd numbers. Even and the odd numbers. Of course, this odd number, you see, it is arranged as odd here, even odd, and just like that. So you are going to have, and this is a union of open sets, and this is also open. So thus, if this is open, then Z1 is closed. Well, if one door opens to another, then it is closed to the other. So now you see here, when this the complement is open, then it means that that set is closed to itself. So with this now, we can come to a reasonable conclusion today. We have treated the Euclidean topology on R1, and you can get some assignments in the text which you have with you. Maybe in the next class, I will just touch another example before we go to the case. So in the next class, we'll still dwell on Euclidean topology on R2, and if time permits, we'll also look at the general one, which is Rn. Thank you.
Finish him. Kill the guy now. You have to come.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
Who is King Kong, sir?
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting for in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have V last semester.
We pounce on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the baby will to have been first born. Stupid boy.